everyone for tuning in. So today I want to talk about science opportunities with or time domain and multi-messenger science opportunities with massive and supermassive black hole binaries in the context of pulsar timing arrays and LISA. So if you joined us for the seminar talk a few months ago, you may remember from Adi's talk how AXIS will be this really powerful observatory for observing dual AGN at kiloparsecs separations. And today I want to talk about observing these sources after they become gravitationally bound. And I will particularly talk about nearly to centiparsec separations, because this is a regime where gravitational radiation would drive the orbital evolution and causes them eventually to coalesce. So these SMBHBs are also strong sources of low-frequency gravitational waves for pulsar timing arrays and LISA. And because these binaries are formed in galaxy mergers and gas-rich environments, we also expect them to emit electromagnetic radiation. So they're also promising multi-messenger targets. And here I'll talk about two flavors of these binary black holes. One is the supermassive black hole binaries of about billion solar masses. And they have orbital frequency or orbital periods between months to years. So they emit gravitational waves at nanohertz frequencies. And this is a regime of the pulsar timing array, which is a gravitational wave detector that is synthesized on the kiloparsec scale using precisely timed millisecond radio pulsars. And these SMBHBs in the PTA band are long-lived sources. So their inspired time scales are much, much longer than the human time scale. So they stay in the PTA band basically forever. And the second type is the massive black hole binaries of million solar masses. And their orbital periods are approximately hours or millihertz gravitational wave frequencies. And they can be detected by the future Laser Interferometer Space Antenna, which will be a space-based gravitational wave detector led by ESA with NASA contribution. And it was recently adopted by ESA back in January. And these MBHBs have a lot of similarities with the SMBHBs, but these MBHBs are like SMBHBs on steroids because they evolve on a much shorter time scale, and LISA can detect them, localize them, and follow them throughout the inspired process and witness the final merger. So in this talk, I want to first give a quick overview of the kind of electromagnetic signatures we expect from these MBHBs and SMBHBs, especially in the time domain and especially in X-rays. And I'll talk about how the observations of those EM signatures will enable multi-messenger science for PTAs and LISA. So I mentioned briefly earlier that we expect these binaries to accrete and shine like AGN. And over the past few years, or maybe a decade, we've made tremendous progress in understanding what kind of accretion disk structure that is around this binary, this binary, and what kind of EM signatures we can expect from this binary AGN. And people do so using hydro or MHD simulations of this kind of system. So this is a snapshot from one of the simulations. So right away, you can see that there are a lot of complex structure in this binary accretion disk. For instance, you see that these two black holes can form their own accretion disks, which are known as mini disks. And these mini disks pull gas off this, what's called circumbinary disk, through a pair of streams. And this circumbinary disk acts like the reservoir that supplies the gas and fuels the binary as a binary AGN. And you may also notice some other features like the low gas density cavity in the middle of the circumbinary disk, and an overdensity of lump in the inner edge of the circumbinary disk. And because of these unique features in this binary system, we expect there to be a range of observable EM signatures from this binary AGN. And most of these signatures fall into one of these two categories. So one is the spectral features. And you can think of them as the EM imprint that the disk structure leaves in the spectrum of the source. So for example, the low gas density cavity will cause a deficit in the UV spectrum, and the accretion streams and the two mini disks will also show up in the X-ray spectrum. And I'll talk about those in just a minute. And the second category seems a little more intuitive. So that's where the binary orbital motion periodically modulate the flux of the host AGN. And currently there are about three mechanisms, periodicity mechanisms, that have been studied by theorists. So one is when the accretion onto the binary is modulated by the interaction between the binary and the lump in the circumbinary disk. And these simulations also find that the exact modulation frequency depends on the binary mass ratio. And in the light curve, we expect to see periodic modulation that is on one or even more frequencies, and perhaps has a sawtooth kind of light curve profile shape. And if the binary is viewed close to edge-on, you will get other effects. For instance, if you picture these two mini disks as light bulbs, the emission from the mini disk will get Doppler boosted as the black hole moves towards the observer along the line of sight. So here in the light curve, we expect to see periodic and almost sinusoidal modulation on the binary orbital period. If the binary is viewed almost exactly edge-on, you will also get gravitational lensing effects. And this is in fact known as self-lensing, because this is when one black hole, one member of the binary magnifies the mini disk of emission of the other member. So here you get these two sharp lensing spikes per orbit. So a few years ago, it was realized that we could search for these SMBHBs that we couldn't spatially resolve by looking for AGN that have periodic variability and infer the presence of binary. And over the past few years, people have done this systematically using large optical time domain data sets. And currently, there are about 200 of these periodic AGN candidates that are thought to be possible binaries. And of course, this also raises the prospects of doing similar types of searches in the upcoming Rubin LSST. And in fact, because of the large volume that Rubin LSST can see, we expect there to be maybe up to a few hundred of binaries with these periodic accretion variability signatures, and maybe a few to a few dozen binaries with Doppler and self-lensing signatures. So what does it all have to do with the X-rays, and where are the SMBHBs selected in the X-rays? The short answer is that there aren't so many binaries selected in the X-rays. Here I'm showing a candidate reported a few years ago, and it was thought to be a binary because it has a possible periodicity in the Swift-Bat hard X-ray light curve. It has a possible double ion line in the Swift XRT spectrum. And if you remember from the binary picture that I showed earlier, the idea is that each mini disk will produce its own broad ion line. And at certain binary phases, the lines can be separated as a double line. So one way we could search for these binaries in X-rays is to look for periodicity in the light curve, just like we do in the optical. Or we could measure the spectrum, the X-ray spectrum, and model the spectrum and look for things like a double ion line. There are also other signatures to look for in the X-rays. For example, these two studies suggested that the accretion streams will shock the mini disks and create bright X-ray emission. And this signature may be brightest in the ultra-hard X-rays, but may be already observable at soft X-ray energies. So some of these studies have looked at the X-ray spectra of binary candidates selected in other wavelengths and model their model their spectra or measure their alpha OX parameter and look for signs of excess. So for example, here, on the right, the black dots are a sample of binary candidates selected in optical based on their possible optical periodicity. And here they calculate their X-ray or luminosities using Chandra data and compared with a sample of quote-unquote normal AGN. So in the 2030s, when LSST starts to find these binary candidates, perhaps due to their optical periodicity, we will need a sensitive X-ray telescope to follow up these sources and look for other signs, these other predictive signatures that could support the binary picture suggested by the optical. And of course, this X-ray telescope doesn't have to be just a follow-up facility. It can also be its own discovery machine if it has an X-ray galactic survey field. And that's because theory predicts that there could be hundreds or even thousands of these binaries in the whole sky with this kind of hard X-ray excess signature. So even with a modest survey field, we could systematically explore this discovery space that's currently completely unexplored. So with those in mind, let's look at what it means for multi-messenger science in the 2030s. As many of you have heard, the pulsar timing arrays have recently seen evidence for a stochastic gravitational wave background that is consistent with the population of SMBHBs. And some studies have suggested that the loudest of them, the ones that are loud enough to stand out from the background, could be detected as single sources, individual sources in the near future, perhaps even within the next few years. And those studies typically take a current PTA data set and project it into the future. But the future PTA is not just the current PTA operating for a few years longer, because in the next few years, the PTAs will undergo major upgrades because of new radio facilities. And for the nanograph PTA, which is the North American-based PTA, that will happen thanks to the planned Deep Synoptic Array 2000, or the DSA 2000, which will be an array of 2,000 5-meter radio dishes. So you will have irreversible sensitivity, but it's optimized for sky surveys. And about 25% of the time on the DSA 2000 will be dedicated to nanograph pulsar timing. So here we used a simulated population of galactic pulsars, and we find that DSA 2000 can see something like 150 millisecond pulsars, which is twice as many the number of pulsars that we're currently timing with nanograph. And those DSA 2000 pulsars will also have excellent timing precision. So the effect of the DSA 2000 can be seen in this figure on the left. So this gray area represents the expected gravitational wave amplitudes of these single sources. And the green curve is the projected nanograph sensitivity to single sources in 2036. So in 2036, we will already be sensitive to a lot of these single sources. But with the addition of DSA 2000, which is now showing blue, we'll be even more sensitive to these sources. So in the mid-2030s, when nanograph and the other PTAs start to detect and localize single sources, we will need EM telescopes to follow them up and look for their EM counterparts. So for example, in the X-rays, we can look for perhaps spectral hardening in the hard X-rays that suggests accretion stream shocks, or perhaps a double ion line that suggests these two mini disks that are attached to the two black holes. Because these SMBHBs in the PTA band are long-lived sources, their multi-messenger observation can go the other directions as well. So we may already be able to detect their EM signatures before we reach the sensitivity to observe them in gravitational waves. And if we can incorporate the EM information about the source in our gravitational wave search, that will give us a boost in detection sensitivity. So here we demonstrate this by injecting a few mock binaries and try to recover them using different types of search strategies. So in an uninformed search, which is the typical type of search that PTAs do, we can't recover the source, which is consistent with the fact that these are relatively quiet sources. But if we use a more targeted approach and use information like the sky location, the distance, the black hole mass, and even the orbital frequency, which we can estimate from observations of the periodicity, and those are all parameters in the gravitational wave signal. If we can incorporate those parameters in our gravitational wave search, we can increase our detection sensitivity by a factor of few, maybe even an order of magnitude, depending on the sky location. And here we see a similar improvement in parameter estimation as well. So if we can detect these sources in any wave band, including X-rays, that will trigger the search for their gravitational wave counterpart in PTA data and help us detect those subthreshold sources that we can't detect using only gravitational waves. So now moving on to multi-messenger science with LISA, which has a planned launch date in 2035. LISA can localize massive black hole binaries within about a square degree a day before merger. And a square degree this sky localization error box can fit comfortably within the field of view or something like Rubin. But as I'll discuss in just a minute, it's crucial to observe these sources in X-rays. And of course, 1 square degree can be covered by an X-ray telescope with just a few pointings. So if this telescope has a relatively large field of view and rapid response time, we could catch these binaries before they merge and observe them simultaneously in gravitational waves and in X-rays. So what do we expect to see in X-rays in these sources? These simulations show that these 2 mini disks that I discussed earlier, they persist almost all the way to merger. So there's still plenty of gas that can fuel the binary at this late in spiral stage. And also the X-ray flux will be modulated on the binary frequency, which is now increasing with time as the binary orbit shrinks. So in gravitational waves, we expect to see a gravitational wave trip as the binary approaches merger. And in X-rays, we also expect to see an X-ray trip as the modulation tracks the binary dynamics. In the moments before merger, these 2 mini disks are finally disrupted. And once they disappear, the X-ray flux will plummet. So that's what we see on the right in green. At the same time, the optical is flat. So the optical is shown in red here. Because that originates from outer in the circumbinary disk and doesn't know about the binary merger. So this shows why is it particularly important to observe these binary mergers. So in X-rays, because when X-rays are seeing these rapid variations, these fireworks, in the binary merger, the optical would just vary, however, normal aging will vary. But this also showed there's a lot of synergy between an X-ray telescope and an optical telescope in these binary observations, because that way we can form a more complete picture of what's happening in the system. So at the time of merger, LISA can localize these sources within about 0.1 square degrees. And that can be fitted or can be covered by the X-ray telescope with just 1 pointing. So the X-ray telescope will be particularly powerful at observing these binary mergers and any after-merger, post-merger afterglows or post-merger emissions. And these simulations show that some of these more recent simulations show that the X-ray flux, which would plummet just prior to merger, will gradually recover in days post-merger. And if the new black hole gets a recoil kick, that kick will perturb the circumbinary disk and contribute to some of this the post-merger recovery. So a question that I haven't addressed is how likely is it for us to observe the flux, the X-ray flux from these black hole mergers? And this question has been addressed in the context of Athena-LISA synergies. So here in this figure, the horizontal lines are the X-ray fluxes of black holes of different masses at different redshifts. So for something like Athena, it can detect the more massive mergers with relatively short exposure times. But eventually the confusion limit kicks in. So that's the flattening of this purple curve because of its far arc second PSF. So Athena would have trouble detecting those smaller, lower mass mergers happening at higher redshifts, even with a few hundred kiloseconds of exposure. And those smaller mergers at high redshifts are thought to be the majority of LISA mergers. So this is where a higher spatial resolution will be really powerful at detecting those faint mergers and witnessing the birth of a new AGN. So I'll just sum up here. The science of MBHBs and SMBHBs is incredibly rich, from understanding the growth and the evolution of supermassive black holes to understanding accretion physics in dynamic spacetimes, to the observations of EM counterparts to low frequency gravitational wave sources. And I haven't talked about the last point in this talk, but these sources also have the simultaneous observation of these sources also have implications for probing cosmology and constraining the propagation speed of gravitational waves versus light. And in this, hopefully, have managed to convince you that in order to explore this full range of science, we would need an X-ray telescope with high sensitivity, a large field of view, high spatial resolution, a survey capability, and a rapid response capability. And of course, that X-ray telescope is AXIS. And that's all, and thanks.
Great, that was really interesting. So while people are thinking about what question to ask, I'll sort of ask you one general question. I mean, I think there's a lot of really exciting things that you can do in the X-rays. You talked about like the drop-off. You could look for periodic light curves. You could look at the hard, excess in the SED, as you mentioned, to confirm optical candidates. Which do you think is kind of most exciting to you? Is it the multi-messenger?
Yeah, they sort of complement each other. If I could go back. Yeah, maybe this slide. Yeah, they really complement each other. And I would say we would want to observe more than one of these signatures. For example, the periodicity would tell us about the periods, the binary period. And if you can observe the oscillation of this double line iron line, that will also help us constrain the orbit. And things like the X-ray, hard X-ray axis that would tell us, that would suggest the accretion stream shocks and tell us how the gas is created onto the mini disks. So I think these are really, yeah, these are puzzle pieces we want to put together with these observations.
Great. So are there other questions? Going to raise your hand, or you can just start.
Tingting, can you go back to the slide which showed the accuracy with which LISA can get the position of the candidates?
Okay, so maybe this one. or-
Yeah, so,
yeah,
okay. So basically, given the axis field of view, it seems like it starts, because there's so many lines, roughly at a day or so, there would be objects for which we'd have a day warning.
Sure, yeah.
Okay, so that's more than enough time to slew to that position in the sky. And
Yeah.
presumably, as time marches on, we'd have a combination of searching over a square degree and the position getting better. So it seems like this is rather different from what we saw a few years ago. What's changed? The positional accuracy seemed to be much better earlier.
So which
Well, I remember a few years ago
Yeah.
when Aaron and I were trying to figure out whether Axis could identify the LISA sources.
okay.
We were working with positional errors of a few square degrees or 10 square degrees. And they were happening, within only hours before the merger. So it made it very difficult to find the X-ray counterpart. But this looks much more promising.
Yeah, so yeah, I'm not quite sure which paper or papers you were referring to, but these more recent studies, yeah, it does look a little more promising. But it also depends on the binary parameters, the mass and the yeah, the localization is better for smaller masses because they stay longer in the LISA band.
If I remember correctly, which is dubious, the peak sensitivity for LISA is around 10 to the 6th solar masses.
Something like that, yeah.
Okay.
Okay. Oh, sorry.
That's it.
Okay, great. So a couple more questions. Rick, did you want to ask a question?
Yeah, on the slide you showed just before with the modulation.
Okay, maybe here or
No, that had the count, the periodicity and the count rate. The one you were showing with respect to the previous question, not Richard's, but the one Mike's.
right here.
Start.
Yeah. Am I interpreting the rate correctly as a few counts per 100,000 seconds?
Yeah.
So you'll get a few counts per observation, maybe a couple observations a year. So you'll have maybe 6 counts or more. I mean, is this practical?
I mean, so this
Rick, sorry, go ahead with thinking.
oh, so these have been binned to monthly.
This is the bat rate, Rick.
Ah, okay. My mistake. Thank you very much.
Oh, okay. So okay, that was okay.
Yeah, it's a few times 10 to the minus 11. So we would have, if we were able to observe it with Axis, we would have some severe issues. So Chris, you want to go ahead?
Yeah, I just wanted to back to the source localization, which I agree with Richard that that's looking pretty encouraging. What would the fluxes of those sources be? I'm just thinking, if we can get on them quickly, how long do we actually have to integrate before we can detect?
Right. Yeah. So that hasn't been looked at by these studies. I mean, the closest estimate was something like this. If we assume they accrete at Eddington, and that's how faint they are. Yeah, so I think this is the best estimate we have so far.
So this would be okay. So this is Athena's flux sensitivity, but these would typically be what 10 to 6 solar black holes at what kind of redshift, like redshift 1 or so, or
yeah. So these are assuming. Yeah. So these are 1 or 2. And I don't remember where I think some of those studies look at what kind of redshifts these are happening at, but I don't have those numbers.
okay. I mean, Again, that's looking quite encouraging, I think. Thanks.